welcome back to another lesson on data structures and algorithms. So, have you ever wondered how Google Maps find the shortest route to a destination? Or how Facebook suggests friends you may know? Or even how airline companies manage thousands of flight routes between cities? The answer to all these lies in a powerful data structure called graph. Graphs are one of the most important concepts in computer science because they help us represent relationships between different objects. However, simply drawing a graph is not enough. Computers need a way to store these relationships efficiently so they can process and analyze them. That's exactly what we'll be learning today. In this lesson, we'll explore one of the most popular graph representation techniques known as adjacency list. Don't worry if you have never studied graphs before. We'll start from the very basics and gradually move forward step by step. By the end of this video, you'll understand what the graphs are, why graph representations are needed, adjacency list work, and how they compare with adjacency matrices. Alright, so let's begin our journey into graph representations. Before we dive into the lesson, let's quickly look at our learning objectives. By the end of this session, you should be able to define what an adjacency list is, understand the concepts of vertices and edges, contrast an adjacency list from a graph, interpret adjacency list representations, compare adjacency list with adjacency matrices, and finally understand the advantages and limitations of using adjacency lists. These are fundamental concepts that will help you to understand advanced graph algorithms later in your studies. Alright, so let's begin with the most important question. What exactly is a graph? A graph is a nonlinear data structure used to represent relationships between different objects. Think of a graph as a collection of points connected by lines. The points are called vertices or nodes. The lines are connecting them are called edges. Let's think about a real-world example. Imagine a social media platform. Every user can be represented as a node. When two users become friends, a connection is formed between them. That connection is represented by an edge. Together, these users and friendships create a graph. Another example is a roadmap. Cities can be represented as nodes. Roads connecting cities become edges. In this way, graphs can be model countless real-world systems. Unlike arrays or linked lists, which store information in straight sequence, graphs follow information to connect in multiple directions. This makes them extremely flexible and powerful. Whenever we need to represent relationships, graphs are often the best solution. Now that we understand graphs, let's ask another question. If we can simply draw a graph on a paper, why do we need graph representations? The answer is simple. Humans understand visual diagrams very easily, but computers don't. A computer cannot directly understand circles and lines drawn on a screen. Instead, everything must be stored in memory using a structured format. Think of it this way. Imagine showing a road map to a computer. The computer does not see the roads and cities the way we do. It only sees the data stored in memory. Therefore, we need to convert visual graphs into format that computers can store, search, and process efficiently. This conversion allows algorithms to perform operations such as finding paths, searching for connections, calculating shortest routes, detecting networks, and much more. Graph representations act as a bridge between the visual graphs and the computer's memory. Without graph representations, graph algorithms would not be possible. So, one of the most common ways to represent a graph is an adjacency list. So, what exactly is an adjacency list? An adjacency list is a representation in which every vertex stores a list of all vertices directly connected to it. Let's break this down. Suppose we have a vertex called A. If A is connected to the B and C, then the adjacency list for A would simply contain B and C. In other words, A keeps track of its neighbors. The same process is repeated for every vertex in the graph. The result is a collection of lists, one for each vertex. This approach focuses only on actual connection. If two vertices are not connected, no storage space is wasted recording that fact. This is one of the main reasons adjacency lists are so popular. Alright, so let's take a closer look at how an adjacency list is organized. You can think of each adjacency list as a small linked list. Each vertex serves as the starting point of its own list. Following the vertex are all of its neighboring vertices. For example, A points to B and C, B points to A and D, C points to A and D points to B and C. Notice something important. Only connected vertices appears in the list. If there's no direct connection, that vertex does not appear. This helps reduce unnecessary storage. Imagine a graph with thousands of vertices but only a few connections. An adjacency list would store only those actual connections. As a result, memory usage remains low. Now let's learn how to build an adjacency list. This process is actually very simple. Step 1. Identify all vertices in the graph. In our example, we have 4 vertices A, B, C, and D. Step 2. Look at every edge. Find out which vertices are connected. We can see the following connections. A is connected to B, A is connected to C, B is connected to D, C is connected to D. Step 3. Create a list for each vertex. Then record all directly connected neighbors. Once every connection has been recorded, the adjacency list is complete. This systematic method works for graphs of any size. Alright, let's walk through a complete example. Suppose we have a graph containing 4 vertices A, B, C, and D. A is connected to B and C. B is connected to A and D. C is connected to A and D. D is connected to B and C. Now let's create the adjacency list. For vertex A points to B and C. For vertex B points to A and D. For vertex C points to A and D. For vertex D points to B and C. And there we have it. The entire graph has now been transformed into adjacency list representation. Notice how compact and organized it looks. Now let's slow down and observe the process more carefully. Start with vertex A. Ask yourself, which vertices are directly connected to A? The answer is B and C. Record them. Next, move to the B. Which vertices connect directly to B? A and D. Record them. Continue the same process for C and D. By repeating these simple steps, we systematically build the complete adjacency list. This method is exactly what many graph algorithms use internally. Now you can see the final result. Each vertex has its own neighbor list. The beauty of this approach is its efficiency. Only existing connections are stored, nothing extra, nothing unnecessary. If a graph contains only a few connections, adjacency lists become extremely memory efficient. This is why large scale of systems often prefer adjacency lists. Social media platforms, transportation networks, and communication systems frequently use this representation. Now let's look at another graph representation method called the adjacency matrix. Instead of using lists, an adjacency matrix uses a table. Rows represent vertices, columns represent vertices. If 2 vertices are connected, we place a 1. If they are not connected, we place a 0. This creates a matrix showing every possible connection. One major advantage is that checking whether 2 vertices are connected is extremely fast. However, there is a downside. The matrix stores space for every possible connection, even if many connections do not exist. This can consume a large amount of memory. Alright, so let's compare the two approaches. Let's talk about adjacency lists first. It uses less memory, excellent for sparse graphs, easy to traverse neighboring vertices, widely used in graph algorithms. However, checking for specific edge may take longer. So the adjacency matrices allow fast edge lookup, easy to implement for small graphs, but require significantly more memory, especially when dealing with large sparse graphs. So which one is better? The answer depends on the situation. For most real-world networks where connection relatively sparse, adjacency lists are usually the preferred choice. Alright, let's summarize the strengths and weaknesses of adjacency lists. So the advantages: they use less memory. They are highly efficient for sparse graphs. They make graph traversal easier. They work extremely well with algorithms such as breadth first search, depth first search, and Dijkstra's algorithm. They scale effectively as graph size increases. So the limitations are finding a specific edge may require searching through a list, and dense graphs can reduce efficiency. Each lookup is slower compared to adjacency matrices. Some operations may require additional traversal. Every representation has trade-offs. The key is choosing the right representation for the problem you are trying to solve. Alright, so we've reached the end of today's lesson. Let's quickly recap what we've learned. We started by understanding what graphs are and how they represent relationships between objects. We learned about vertices and edges, the building blocks of every graph. We then explored why graph representations are necessary for computers. After that, we studied adjacency list, learned how they structured, and walked through multiple examples of constructing them step by step. We also compared adjacency lists with adjacency matrices and discussed their advantages and limitations. The most important takeaway from today's lesson is this. An adjacency list stores only the actual connection in graph, making it one of the most memory efficient and practical graph representation techniques available. As you continue learning data structures and algorithms, you will discover that many famous graph algorithms rely heavily on adjacency lists. So understanding this concept now will make future topics much easier to learn. Thank you so much for watching. If you found this lesson useful, please like the video, share it with your classmates, and subscribe for more tutorials on data structures and algorithms. Until next time, keep learning, keep practicing, and keep exploring the fascinating world of computer science. See you in the next lesson. Peace.